So we're going to look at laser testing methods today, optical laser testing. And for this one, I'm going to look at three different methods. So we're going to start with holography, and then shearography, and finally profilometry or profilometry. So these are all related in some ways, but they use laser light in slightly different ways in order to perform very high precision measurement of surfaces. And so where we used this kind of stuff, and I've performed profilometry. I've never done holography or shearography, but the profilometer we had was used for skin inspections most of the time. And the biggest time we'd use it was after a hail strike. So if an aircraft flew through hail, or if an aircraft was on the ground and got hit by a hailstorm, you would have a lot of little dents all over the surface, and those would all have to be mapped and analyzed. That would have to be sent to either our engineering department or back to the manufacturer's engineering department, depending on the extent of the damage, in order to get what were called repair engineering orders or repair engineering authorizations. Whether it was a case where we could continue to fly the aircraft indefinitely, we could fly it for a period of time before making repairs, or if there were certain repairs, temporary repairs to allow us to fly it to like the next C check where bigger repairs could be done, or if it had to be taken out of service and repaired immediately. And so it was important because before we had this kind of equipment, we had an incident where it was about 40 to 50 aircraft on the ground in Denver, and a hailstorm came through and basically caused dents on all those aircraft. Tops of the wings, tops of the fuselage, tops of the horizontal stabs. And it took several weeks of basically unlimited overtime with the company flying anyone that wanted to go to Denver to work double shifts, one after another, just dent mapping the entire airplane in order to get the airplanes back in service. Whereas something like a profilometer, you can scan, and that is, you have to measure each dent. How deep is it? How big a diameter? What's the width versus the diameter? How close is it to every other piece of structure around it? Ribs and stringers and frames and formers. How close is it to other dents in the same area? Is it in an area that's critical for things like airflow, like pedostatic, or things that could cause oil canning due to pressurization? And then, that all those measurements have to be collected, diagrammed, put together, sent to the manufacturer, where a profilometer can scan the surface and basically send that map down to the 10,000th of an inch measurements directly, as a data file to be analyzed and quickly dealt with. So that's what these are. So holographic testing is the first one we'll look at. This is also called holographic interferometry. So interferometry, interference of light. Part surface is mapped using a holographic technology. And the comparison in this case is one where we have to compare how a surface appears at rest versus under a stress. So when stress occurs, it's going to change, the surface will flex or move or deform in some way. And the holographic interferometer will be able to pick up those changes in order to map what that surface looks like. And so those discontinuities will appear, they'll show up due to differences in how the material deforms when stress applies. Basically, the holographic image that's produced will be different for the unstressed part than it will be for the stressed part. And you can compare, those two images are compared to find and make measurements for shape and discontinuity and other things like that. So when we're talking about stress, there's different ways it can be done. Mechanically, heat, heating or cooling. Heat is adding heat or taking heat away. Pressure, something like a fuselage, you can even pressurize or put into a pressure, some kind of pressure environment. Vibration, vacuum, lack of pressure, other things like that. And that stress causes the deformation, and the deformation is going to be inconsistent in those areas where there might be damage. Or you might have underlying delamination in a composite structure. An area that's not as strong is going to stretch more or deform more than an area that is stronger, that still is stronger. And so that underlying structural condition is going to play a role in how much deformation takes place. So the theory is holography is relying on interference patterns in light, and that's due to changes in light wave phase. So light, going back high school physics, light acts as both a particle and a wave, and it's getting more in depth than what we probably are going to, get into here learning about, but you've probably heard about that. So when you get two waves that are in phase or out of phase with one another, you can get constructive and destructive interference, just like we saw with sound waves, right? When you get two waves that are in phase where the peaks are together, when you add them together, the resulting peak gets bigger, the resulting trough gets lower, or when they're in opposite phase, they can cancel each other out to some extent. And so with light, that creates dark and light areas from the interference pattern. And this is demonstrated with something called Young's double slit experiment. In the next two slides, I've got videos. But before we get there, holographic testing, how this is different is it's similar in some regards to photography in that you're taking an image, but photography, light, you're recording intensity, or you're recording intensity of different colors, right? In holography, you're recording intensity and the phase. So this is where the laser part comes in, as a laser produces light that is all in phase with one another. All the light is going in one direction. And that's why a laser, travel, you can't see it in the air, but then you see it on an end. There's essentially no light escaping or phases escaping out to the side. Everything's in line going that direction. Okay. Until it hits something, like the wall here, and then it scatters and we can see, you can see where that laser is hitting a surface. So we're doing the same thing here with our testing. So that's kind of the theory behind what happens. So now if we actually put this together into an instrument that we can use, the process is, what we have happening is the waves we have, so the laser I mentioned produces a light source where everything's in phase. So light's produced in phase. So that's why we have in a single phase by the laser. That's why we're using a laser. But then what we're going to do is we split the light into two beams, and that's done through a beam splitter, which is kind of a partial mirror. It reflects a portion of the, you've probably seen those films, like the films that are kind of reflective, but you can kind of still see through them. So it's that same kind of a mirror beam splitter. And what's called the reference beam is reflected off of a mirror or directed directly to our object. Okay, so that's our reference beam. So that's going to stay, that's going to be in one phase. It's going to maintain one phase. And then, that light is going to hit the object, and that, just like when I put the laser against the wall, the light from my laser's hitting that, it's reflecting off to your eye. Here, that beam is going to reflect off the object, and the holographic plate is going to see that in a way, right? So it's going to see that light coming off the object. And when that light from the laser hits the object, just like when my light from my laser pointer hits the wall, part of what allows us to see that is that it's scattering that phase. So now the light is no longer all in a single phase, not all traveling, the waves aren't all aligned in one direction. And so, you're getting now a beam of light coming from the top in this image that's coming to the holographic plate, which is essentially, a holographic plate is kind of like it's like film or a detector, an electronic detector, that is going to be it's going to track the intensity as well as the phases of all the different portions of light that are hitting it. Okay. So it has polarized filters on it that can kind of sort out the light. What light's going up and down, what light's got a phase left and right, any different angle. It's able to kind of track both the intensity and that phase. And then you have what's called a reference beam, the other beam that came off of that splitter. It's just going to be reflected directly to the holographic plate. So that kind of has the original phase in it. And so that holographic plate is going to be comparing the intensity and the phase of the light, across locations. So, originally it was this, this is what it would come as, and, but it's being changed when this other beam mixes with it. So some of those areas where those light beams come together, now that they're no longer in perfect phase with each other, some of those, beams of light, beams, I guess, coming off the object, and some of those off of the reference beam are going to be in phase with each other. That'll create higher intensity spots on this holographic plate. And some of them will be out of phase with one another. So those will create, low intensity spots on the holographic plate, and then any various, combination in between. And so what you get is a image that looks like this. So those, again, those beams out of phase are going to create kind of the darker areas, and the beams that are in phase are going to create the lighter areas. And you get what's called a holographic interference pattern. And that gives you a measurement, that gives you a kind of almost like a topographical representation of the surface of whatever it is you're imaging. And so then what we do, this is, you're going to take two of these holographic images. The tester is going to do this, and it does it pretty much automatically. Most of these are automatic. It's going to take one with the part not stressed, and then it's going to take a second holographic image with the part stressed, and it's going to compare the two and see what changes. Okay, because, this doesn't mean you have dents on this part. Maybe the part does have some kind of a contour. Maybe the outside of the airplane is supposed to look like a golf ball. I don't know one yet that's supposed to, but I worked on airplanes that looked like golf balls on the outside. As long as there was damage under a certain amount, that was okay. But, I don't know what it did for wind resistance like a golf ball. But as long as engineering said it was good, I never had a catastrophic depressurization while I was there, so I guess it was good. But, this can compare. So something like a dent, right, oil can when you pressurize the plane, and over time that can work harden the material in that area and can cause cracks to form. So, this would allow you to pick up, how much deflection is taking place when that airplane's oil canning. How big of a dent is it? What is the actual diameter and depth of that dent? And when you lay those on top of each other, you can actually create it's a 3D, it provides a 3D representation of the object. So, what most people have seen are holographic kind of, the little hologram things in, books and little toys and stuff like that, where essentially you have the holographic plate here it's an image created with different kind of polarizations in the material. So it's allowing different orientations of light to pass through, or reflecting different orientations of light in different areas. Okay. So that's where you get what's called a diffraction gradient, and with our laser, it's going to be the phases are going to be modified in the same way that you see, when you're looking at a visible hologram. So, which results in this virtual image, and we're comparing those two virtual images in order to inspect our part. I guess I got a little ahead of myself. This is all, for the most part, done with computerized systems nowadays. You really don't see a case where here's two holographic images, put up one, put up the other, put up one, put up the other. You're not playing the game like when you go to the eye doctor and they're like, is A better or B better? A or B, right? We're not doing that. We're putting them in a computer, and it's comparing the intensity at each pixel and able to make, a judgment, or able to analyze that for different interference patterns. The advantages of this is we can have very precise measurement, down to the 10,000th of an inch. okay, or less than 10,000th of an inch. It, in many cases, is non-contact. The measurement device itself is shining a laser beam on is shining lasers on a surface, so there's no physical contact there. The stress source can also be non-contact. Think of like pressurizing the fuselage of the airplane or provide a heat source, right? It may not have to actually touch it. You can use something like a heat lamp, or what most of these holographic imagers use is a flash source. So they take an image, without the right before the flash, and then it does a flash that causes a very slight amount of heat, just like in thermography, flash thermography, and it takes the second holographic image during the flash, and then can compare, the changes. And so the stress source can be non-contact, making it have a very low chance of damaging whatever it is you're working on. Disadvantages are there are still possible material damages. If you overstress the part, you can damage the part. If you put too much stress in it, that's not good. It's a complex process, and the interpretation pretty much has to be done by a computer. This isn't something that is done by a person, and so you have to, there's a lot of research and work that goes into developing these tools, which makes them fairly expensive. The other thing about it is it's very sensitive to motion. Any little, you're measuring to the 10,000th of an inch using optics. Any little tiny movement is going to throw that off. So motion, vibrations, and that kind of thing. And then the other part is thermography. We learned about diffusivity. You can also obscure, if you have different diffusivity areas that will absorb, and emit the light differently, the laser in different areas, and so that can cause there may be limitations on what you can image, especially if it has different surface treatments across the part. Okay, so that kind of wraps up holography. The next technique we're going to look at is shearography, and this is very, very similar, but with a couple key differences. So here, similar, it's mapped the same way. So when we perform shearography, it is another laser testing method. Again, the part has to be mapped, unloaded, and stressed, just like with holography. And here, again, is it's going to change light. Discontinuities will be visible due to differences in how the surface materials deform when stress is applied. And then it's going to change the light. So it's a similar process to holography. It actually grew out of holography. But here, instead of just the two images, it uses something called laser speckle pattern interferometry. And so rather than using a cohesive laser, in this case, we're going to project a speckle pattern, a non-cohesive light onto a surface. So you've probably all seen, if you look at something shiny, sometimes it's hard to see contours on a surface or see things, right? But if you, or just under regular light, but if you shine a light or a shadow from the side, you might be able to see different, surfaces, right? Or different changes or undulations in the surface. This is kind of the same thing. If a surface is hard, if it's hard to see, it's to help to magnify any changes in the surface by overlaying a speckle pattern while performing a holographic inspection. So again, we use a laser so that we have coherent light, all the lights in a single phase. It's also monochromatic. It's a single wavelength of light. Okay. The laser is projected on the surface. So now instead of splitting the beam, the laser is projected directly on the object that we're looking at. Okay. But that laser is going to have a speckle pattern to it. Okay. And now when that light hits the surface, it's going to change its phase and intensity across the surface in different areas. Okay. And then here we use a camera, a special camera, that is able to detect phase of light in addition to intensity. So that camera is able to pick up on those areas where you have phase interference, positive or negative. phase interference that causes an increase in intensity, or a phase interference where it causes a decrease in intensity. And that creates that speckle pattern that we're going to then analyze. And that's going to go into, it's going to be a software system. So you can see here a laser off to the side, a shear graphic sensor, and typically there's what's called a shearing device, which is a set of polarizing filters. That's built in this case, it's built into the camera. It's a camera with special polarized filters on it. And again, the images are taken object at rest, object under stress. And they're placed next to one another or on top of one another, or a computer goes pixel by pixel to analyze differences in order to create a map, kind of a 3D map of what that surface looks like. Again, it's almost like a topographic type map of the surface. So shearography advantages, like we saw in the video there, it's very fast. It can scan upwards of 1 to 2 square meters per minute, or per second, excuse me. So you can do a very, very large area very quickly. Again, it's very precise measurement, down to the 10,000th of an inch. It is able, I don't have it here, but where the limitation with holography is that if you don't have enough of that definition in the surface, like I said, where sometimes you have to take like a flashlight and shine it down the side to see a dent or something like that, shearography is able to pick up some of that stuff that may be harder to see, especially on more reflective surfaces or surfaces that are lower emissivity, because it does, create its own kind of pattern, so to speak, overlay on the surface. Disadvantage, well, and it's non-contact, just like we had with holography, similar issues with, not having to contact the part, but also, you don't want to damage the part during the stressing process. Oops. Disadvantages, possible material damage if you over apply the stress. Surface roughness has to be 1 wavelength of light or more. So it's limited if you're looking for very, very fine. This is more like surface finish type analysis in the manufacturing world, right? There may be some limitations depending on what wavelength of light your laser is. Again, another complex process with interpretation that's going to require some kind of specialized computer and software and equipment to go with it. And it's fairly expensive. Now, laser speckle interferometer or shearography can be sensitive to lighting conditions because it has to produce that speckling pattern on the surface. If you're in a very bright area, you won't get the darker area. You won't get the dark spots on the surface. And so it has that. And there is some motion, again, just like holography, motion in the environment, vibration can be an issue. However, it's not quite as sensitive as holography. So again, shearography grew out of holography and was to kind of overcome a few of those limitations that we had with the older technology. The third laser testing method we're going to look at, and what's probably the most common in aviation, is profilimetry. And this is probably the easiest to understand because it doesn't deal with the whole lasers and splitting the beam and phase changing and all that kind of thing. So in this case, it's basically 3D optical scanning of a surface. So you have, or surface profiling. So the part is scanned using an optical method, cameras or sensor arrays of some kind, to produce a topographical map. But in this case, the part doesn't have to be stressed. It's purely to see the, what does the part look like right now while it's sitting here. And that's where this was very useful in mapping out, 1,000 dents on an aircraft where it got hit by hail or flew through a hailstorm. And so here the scan is, it can be a point, a line, or an area. And it can find things like morphology, which is the kind of the profile of curvature or surface undulations. Cap heights, roughness. Okay, roughness, again, probably more of a manufacturing thing. But here, essentially, light is shined on the part, and it's converted to a distance from the sensor by its relative intensity and the location where it hits on a sensor. So, light hitting a surface I'll show it in a minute, but if I'm hitting if I'm reflecting off a flat surface, right, it's going to hit one area. If I go off of so here's my surface, and you'll see a diagram like this in a minute. Let me kind of angle it more. Right, so if I hit light from one surface, it's going to bounce off here. So if I have a group of sensors here, right, this point is going to hit here. If I come here, that point's going to hit there, right? Same distance apart as those. But if I hit, right next to this, right, this is not going to reflect straight out an angle. It's actually going to hit a little bit closer here because of the angle of that area changing. And so that's what I mean by location on the sensor is as that laser scans over the area, it knows how far the laser has moved. So the point should move a certain amount on the sensor. And if it moves kind of the wrong direction or too far or too short of a distance compared to how far the scanning tool moved, then it knows that there's some kind of a change in the topography of the surface or the angle of that spot that it hit. So here's that flat, like I just kind of showed there, and you can see, if light's hitting right here, it's going to go to one part of the sensor. If light is hitting further down, an object further down, it's going to go to another part of the sensor. So that's that location portion. Intensity based on how reflective the surface is. Or here's similar to what I did on the board, where it does this over, right? You have a three-dimensional peak sticking up. That's going to create kind of a two-dimensional. You can see here the laser is coming from inside the screen. The image sensor is closer to you as the audience. So it's going to, that peak is going to reflect there. It appears further away from you on the image sensor, further away from the front edge. So here is another example or an example. So just advantages of profilimetry is, it's a very fast, you can do a large area very quickly. And so again, this was for the purpose of dent mapping over a large area. This was very beneficial. It made the process much quicker. Here, I talk about the ones you saw there for surface treatment to the 10,000th of an inch. Again, the ones we would use in aviation, you're going to sacrifice some of that precision, go to the 100th or 1000th of an inch, but scan a much larger area much more quickly. And again, no contact, no stressing of the part. So there's very little chance of causing any kind of a damage. Disadvantages, though, is translucent or highly reflective surfaces. Can make it hard to image, right? You see reflections and things that can throw off the camera that's looking at the light. So you gotta be careful of that. Ours were sensitive to movement in the environment. That made it a little difficult using them outside. If it was windy out and the plane was kind of moving around, it could cause some issues with it. And so typically we tried to pull them into the hangar to do this. And then we had to be careful that nobody was like walking up and down the stairs or doing anything on the plane while we were trying to take these profilimetry images. And then the surface has to be clean. That kind of goes without saying. If you're trying to inspect a surface, it's probably got to be pretty clean. Otherwise, all you're going to do is get an image of all the little dust and dirt particles and any buildup that's on there, which isn't going to give you an accurate indication. So that's the last of the slides. I'll go ahead and just run the videos